Got it. And you're going to mute everybody now, Ken?
Okay. Okay.
Okay, good. Well, welcome everyone. Wonderful turnout. This is the Midland-Penetanguishene Field Naturalists monthly talks that we've been having online because of the pandemic. And we're delighted to see so many people out. This is obviously a topic of interest or a speaker of interest or both. And we're expecting snow flurries or snow squalls. So it's kind of nice to be online. I have to admit, we don't have to worry about the traveling. So again, welcome everybody. This is going to be the Geology of Georgian Bay. And our speaker is Professor Nick Eyles. Ken will be introducing him shortly. Before we get into the presentation itself, our club member Dave Shandlin would like to say a few words about the Christmas bird count, which is coming up in just over a month's time. So Dave, I'll put it over to you.
Okay, thank you, Susan. Okay, this year the bird count will take place on Saturday, December the 18th. I know that's a little bit close, but it has to be the 18th. It can't be, I guess, an earlier Saturday than that, just because of when I guess the count has to be done. So last year was kind of a funny year because of, I guess, COVID. So what I did last year, which I guess which seemed to work, before I had about 10 areas, and I usually have about say 40 people take part, and you know, everything works well. But of course, last year that wasn't I guess possible. So what I did was I broke the areas down a bit more, so that there'd only be I guess maybe 2 people per area, and I guess that seemed to work out okay. Now this year we're sort of in the same situation, but at least this year I guess nobody could really start to get their vaccinations till about January or February, so at least we have that you know, advantage this year, that I guess that hopefully everyone I guess taking part will be vaccinated. So what I really have to do right now is I guess just people let me know whether they I guess want to take part or not, so I can get up to my numbers. And then after that I guess it'll be up to me to find out whether people are I guess comfortable this year I guess traveling together in some vehicles, or if they would rather walk, or I guess however they want to do it. Other than that, I know we talked about having a Zoom meeting, I guess the Tuesday after the count, and that I guess people were going to send me their results online. That's fine, but I really would like to get back the I guess the tally sheets and I guess the maps, you know, so that I have them for other years, so I don't have to I guess remake them every year. So if possible, at some time during, say, maybe Saturday or Sunday or something like that, if people could drop the results to the Y-Marsh, even though I have them another way, I mean, that would be a way for me to get back the maps and whatnot. So I guess that would be appreciated as well. So people can let me know either by our, I guess, email address, which is, I guess, scanlon@simco.net, or I guess they can call us here. It's 705-526-8320. And I'll just have to play it by ear. Like, I'll have to see how many people we have. And at this point in time, I'm not really asking people what their, I guess, status is. I'm just sort of hoping that, you know, everyone's vaccinated. But yeah, we'll just have to see how it goes. And I've, I guess, been talking to Ken a bit about it too, and I think we can, I guess we can figure it out, I guess the same as we did last year. And yeah, I don't know if anybody's got any, I guess, questions or, I guess, suggestions. I'm open to that as well. But right now I'm just looking for, I guess, numbers so we can, I guess, see how to, I guess, proceed from here. So I think that's all I have, Susan, unless anybody else wants to I guess have a suggestion. Okay, otherwise I'll just leave it at that, and we'll just I guess keep in touch with people as we get, I guess, nearer to the day to see, I guess, how we can handle it from here. So thank you.
Okay, thank you, Dave. And hopefully we'll get a good turnout for that. And I'm going to hand it over to Ken now to introduce our speaker for tonight.
Okay, am I on screen? Or let's see. You got to figure out how to unpin Dave, I think. Okay, I think I'm on screen now, right?
Yes.
Okay, and sorry about the delay there, but just to introduce our speaker, I'm just going to read his introduction from his beautiful book here that he did a few years ago when he was serving on the board of the Georgian Bay Land Trust. And it tells you a little bit about Professor Nick Eyles here. Let's see what it said. Nick Eyles is a professor of geology at the University of Toronto since 1983 and has published research on the geology of modern and ancient ice sheets from the Arctic to the Antarctic. He has written 5 best-selling books, including Canada Rocks, and was host of the very popular Canadian Broadcasting Corporation's 5-part Geologic Journey World Series, which aired on the Nature of Things in 2010. He's been honored with the Geosciences and the Media Award by the American Association of Petroleum Geologists, the McNeil Medal by the Royal Society of Canada, and the E. Ward Neal Medal by the Geological Association of Canada. Nick cottages at Carling near Parry Sound in Georgian Bay. So with that, I'm going to see if we can turn it over to Nick. Fire away, Nick. You've got to unmute yourself there. Hit the little microphone button. We're seeing your screen fine now. But I think you still have to unmute, Nick. You've got to find that little microphone button and unmute yourself. Let's see, see if I can do that for you. I've asked you to unmute somewhere. I think, no, you're still muted. There should be a little microphone button that you press to unmute yourself.
All right. Yeah. Thanks, Ken.
Got it? Okay.
Can you hear me okay, everybody? I hope everybody's comfortable.
Yep.
We have a lot of Earth history to go through tonight, so I'm either going to speak very quickly or leave a lot out. And in fact, the good news is I'm going to leave a lot out. So you can probably tell from my accent that I'm not from around here. I'm from central London, and as a teenager, geology for me was a way of getting out of the big smoke. And I came to Canada as a young graduate student. I was 21 years old in 1974, and I came to Newfoundland. Newfoundland then was in the epicenter, as it were, of the plate tectonic revolution, and I'll touch on that later on. It has great bearings on Georgian Bay. And this was a time when geologists had finally figured out how planet Earth worked, and Newfoundland was one of the places where it showed clearest evidence for ancient plate tectonic movements. But my field area was in northwestern British Columbia. So I would get the bus from St. John's all the way to Port au Basque, cross over to North Sydney, get the train in Montreal, get the bus all the way across to Prince Rupert, and then another bus up to my field area, which was a place called Stewart, right in the far northwest corner of BC, right on the Alaska border. So I saw a lot of mountains. I did the trip several times. But my favorite place was Georgian Bay. It had a spirituality and a serenity, which I didn't find in the mountains. I thought the mountains were rather harsh. So I was attracted to the area. And then I came back to Canada permanently to the University of Toronto. And once again, I found myself attracted to Georgian Bay. I have kids, they're now in their 30s, and we've spent many happy years camping up at Gilbert. We now have a cottage up there, a very small one, and it's a special place. So it's a great pleasure. Thanks for the invite to come and talk about a very, very special place. And the purpose of tonight is to tell you how special it is. So in terms of the geology, I think you're all probably aware of the fact that Georgian Bay really occupies a front line. It straddles the boundary between the Canadian Shield on the east and the north, and the Limestone Plains to the west and the south, so-called Bruce Peninsula, where we see the Niagara Escarpment. And there's a major contrast between the rich agricultural soils down in the south, because we've had glaciations, they've moved sediment around, and we have prosperous towns, Owen Sound, Collingwood, Midland, Penetanguishene, and so on. And then you get onto the Shield to the east, and you have Parry Sound, and it's virtually empty. So most people are aware of that basic contrast, but let's dig a little deeper. And you've got 4 fingers. So let's start with these 4 layers that we see in the geology. And the oldest one, we will start at the base, is the Canadian Shield. And as I'll explain later on tonight, it records a very complex, very long history of growth. Continents grow through time, and some of the best evidence anywhere in the world is to be found around Georgian Bay of what we call continental growth. So we have in the gray at the bottom there, we have the Shield, and this is a section just south of Georgian Bay. It still works for the bay itself. The bay has been scooped out and eroded into the rocks by Ice Age glaciers. But we can see the Shield rising, so we have the exposed Shield, cottage country, lots of trees, lots of forests, no farms. And then that surface, the actual Shield surface, doesn't end in the south. It continues down underneath the overlying much younger sedimentary rocks. And you can trace that surface, which we call an unconformity, by the way. If you think about the rock record as a hard drive on a computer, it's an unstable hard drive, so it records for millions of years, and then it stops recording, and we get these breaks. And these are called unconformities. So that unconformity on the top of the Shield, you can trace down and down to the west. And you can trace it as far as Mexico. You can trace it as far as Calgary. And for those of you, many of you have probably been to the Grand Canyon, gone down to Indian Gardens onto what is called the Tonto Platform and looked down into the gorge of the Great Colorado River. You're actually looking at that same surface. So there's a chunk of the Canadian Shield exposed in the Grand Canyon. And we're going to take a group down there next year and reclaim it back for Canada. Anyway, sitting on top there is what we call layer 2. And this is a scheme for simplifying the geology of this area. So layer 2 is made up of sedimentary rocks. And they're relatively easy to examine because they have fossils in, and geologists can use different types of fossils to match layers. It's a process we call correlation. So these are relatively easy to work on. They're much younger. I've got some dates up there now. There's a shortening there. Millions of years is referred to as mega annum. So MA, whenever we see MA, we're dealing with billions of years. And then billion is giga, like gigabytes, giga-annum, so that's GA. So the shield around Georgian Bay and to the south records an immensity of time. It's about 1 billion years to 2.5 billion, in some places older. And then there's a major unconformity, and then we find the sedimentary cover rocks much younger. And then huge gap again, for which there's no record in southern Ontario. There's been a lot of erosion, a lot of loss of rock, and that had enormous economic implications in the 1860s, which I'll tell you about later on. Sitting right on top of the sedimentary rocks are glacial sediments. So if you go out in your backyard and dig, you'll be digging into soil, and that soil is formed on glacial sediments. It's not formed on rock. It's a result of repeated ice age, ice sheets that have invaded southern Ontario and got down into the States. So they're less than about 2 million years old. That's peanuts to a geologist. And then we have the built landscape on top. That's the stuff that we do to places. So all the little towns, big cities have to deal with this legacy of contaminated material that's been dumped and used as fill. And geologists use the same techniques to examine that. What's the distribution thickness? What's the chemistry? In order to deal with it. So every city, every town has a problem of this built landscape, but that's not what I'm going to talk about tonight. So it's rather interesting individuals that have worked around Georgian Bay, and the first work was done just after 1842, when the Geological Survey of Canada was set up, funded in part by Molson Brewery. I like that. It's not because geologists drink a lot of beer, they do, but it was Molson Brewery consumed enormous volumes of coal, as did the other breweries. And so there was this impetus to find coal. And that was the first task of the Geological Survey under the director, the first director, Sir William Logan, who was a Scot brought across. He'd worked on coal in Scotland. He was the first one that understood how coal formed. He found these upright tree trunks in coal seams and realized that coal was the remains of organic material that had been compressed or the water driven out and so on. So he was an expert on coal. And he produced this famous map, 1865. That's a key date. He named the Laurentian region. That's what we call the shield. That's that sort of limey colored stuff in the north, all old Precambrian rocks. And then recognized the cover rocks of Cambrian and younger material sitting on top. Now you've got to realize that the province of Canada, that included Quebec, which is below Canada, and now Ontario, which at that time was Upper Canada. But the message he took home to his bosses in Montreal wasn't a good one. There was no coal in Ontario or Quebec, and that's because all the coal-bearing strata have been eroded. And at that time, all the manufacturing industry, Toronto, Montreal, imported its coal from Pennsylvania. So we were dependent on American energy. This is the time of the Civil War with big armies roaming around in the South. And there was a lot of concern that unless Canada was brought together as a country using Nova Scotian coal, we'd be taken over by the Americans. So Dawson's map identifying no coal, it's almost a straight line between Georgian Bay and Confederation. And Confederation was the response to the famous no coal problem. So they identified the Laurentian region, which again we call the Canadian Shield, and they were horrified actually at the rocks because there were no fossils, so they referred to it as azoic, without life. And they looked at these big folds and they assumed that these had been volcanic rocks that had flowed like lava that you see in the Canary Islands just recently in Hawaii. And so they referred to the Laurentian area, the shield, as a magma ocean. It was simply the hot outer skin of the Earth which had cooled, and you see evidence of flowage in the rocks. And they left it as that. And the next stage was really led by Logan again, He was a booster for getting people up on the shield. And again, it's at a time when there's big armies roaming around south of the border. So there's a need for bums on seats, boots on the ground. There was a need for immigrants in southern Ontario. But the problem was, of course, that all the farmland had been used up. And the only possible land that was then available was up on the shield. So he was a big booster for colonization roads that crept up onto the surface of the shield. They're still there. I really enjoy rediscovering some of these roads. Some of them are paved over, they're main roads now, but others are no more than gravel tracks. And people came over from Europe under the Free Grants Act 1868, and they were given rock to farm. And there's some very sad stories about the so-called Road of Tears, where people lasted for a year. They used up all the lumber, the white pine, then found you couldn't farm what was left, and they left for Manitoba on the railway. So Logan is a major figure, not just in geology, but also in the population of southern Ontario. And then Alexander Murray, he was a redundant British naval officer. There were many of these types. They were trained to do surveys, topographic surveys, bathymetric surveys. They were scientists, basically. And at the end of the Napoleonic Wars in Europe, they were out of work. There wasn't any need for a big navy. And so many of them came to Canada and they took up farming. They got bored. They'd lived lives of adventure. And they took up geology. And Alexander Murray worked around Georgian Bay. He discovered many of the fossils there. And again, confirmed that there was no coal, and moreover, there were no minerals. And I'll explain the reason for that later on. In case I forget, somebody make a note to ask me why there are no minerals around the shores of Georgian Bay. There's a very good reason for that. And that was first identified by Alexander Murray. And then the next character to come along working on the geology of the bay was a University of Toronto professor called Arthur Philemon Coleman. And he, like many of his generation, had to go to Germany to do a PhD. Germans were the leaders of science, technology, chemistry, and for the geologists, they developed new high-powered microscopes. So for the first time, you could cut very thin sections of rocks. You could polish them to very thin, almost transparency, and you could put them under these new German-made microscopes. And for the first time, you could look at their mineralogy and their composition. And Coleman's great contribution is that he recognized that these were metamorphic rocks. They weren't igneous rocks on the shield, they were metamorphic. So if you know all your rocks from high school, metamorphic, igneous, and sedimentary, metamorphic rocks are pre-existing rocks that have been subject to great heat and pressure, and they've been altered. So that was a great step forward in understanding the origin of the shield. It wasn't complete. He also mapped the nickel deposits and the copper deposits around Sudbury. And if you know anything about the history of Sudbury, nickel was regarded as a contaminant. The word nickel comes from German, meaning the devil, Nick himself. And it wasn't until Cronstedt, Danish chemist, was able to extract nickel that the copper deposits could be worked. And around 1908, this launching of HMS Dreadnought in Britain and the arms race between Germany and Great Britain, and this insatiable demand for armor plate and nickel. And that's when Sudbury takes off, and that's when there's been renewed interest in the geology of Georgian Bay to answer this question: is there any more copper? Is there any more nickel around the bay? And of course there isn't. But it was a huge stimulus, armor plate, to geology around Georgian Bay. Next slide. There we go. Okay, anyway, the next character, and this is a really monumental gentleman in the history of geology, John, or Jock, sometimes known as Jack Tuzo Wilson. And he was a professor of geophysics at Toronto. He combined geology and physics to develop instruments for exploring for hidden minerals. And he had a very interesting wartime career. The gentleman on the left, if you look at the top right there, the gentleman on the left who Wilson is talking to is General Andy McNaughton, who was a physicist and believed that by applying physics to warfare, you could save lives. And it was a very popular political idea in the Second World War. And Thurs Wilson signs up as a so-called sapper in the Canadian Army, December 1939, and then has a most interesting career of testing equipment, training troops in geophysics. The bottom diagram there is a tank trap which had been blown up by what were referred to as McNaughton tubes. And these were steel tubes that were pushed underground, filled with nitroglycerin, and then could be blown up. Very, very interesting wartime career, but he's the guy that develops plate tectonics. And he had a cottage at Go Home Bay, and he brought a Chinese junk back from Hong Kong when it arrived in Toronto Harbor and was dropped into the water from a freighter. It made all the headline news, and he kept it in Georgian Bay and used to sail around Georgian Bay. And he was stimulated by the highly deformed rocks that he saw around him in the bay. So again, there's this connection between the rocks around Georgian Bay and the bigger history of geology. And I have to, this is a bit of shameless self-promotion here. I do apologize. I lead rock walks every summer on the islands, in the 30,000 islands area. And you get a great turnout. We have a great time talking about rocks and so on. And one year I was introduced to this very sprightly lady called Susan Wilson, and it's the daughter of Thurs. And we had a long conversation, and I learned that no one had ever written a biography about this great geologist, and the autobiography that he'd written was a mere 150 pages long. It didn't touch on his great discoveries. So I have to blame my wife. She heard about this story and she said, well, why don't you write a book on Thurs? So I did, and it's coming out next year. So I won't tell you more about what's in the book because I'm going to let you buy it. But anyway, the unlikely revolutionary of plate tectonics, that refers to the fact that Thurs Wilson did not believe that continents could migrate. There was this great debate in geology since 1915 when Alfred Wegener, who was a German astrophysicist actually, proposed that continents drift. And it set off a 50-year-long debate between permanentists who believed that continents were fixed, didn't move, and then the mobilists who argued that there was good evidence that the continents had moved, that once they'd been together and had broken up. And Thurs was firmly in the permanentist camp until quite late in life, and then had a sudden revelation. So that's what's that about. So this is a modern view of the planet. It's a plated planet. It's like crazy paving, but the individual paving stones can move around. They interact in very complex ways. There's about 7 large plates. As you can see on there, the Eurasian plate is the largest. North American plate is also large, as is the African plate, and the continents are basically embedded in the plates. And these are moving around. The arrows are what we call vectors, so they give the direction of movement and also the velocity. There's a little bar down there that's got 5 centimeters a year. So if the arrow is less, it's less than 5 centimeters, and if it's more, it's greater. But in general, they move about the same amount every year as your fingernails grow or your hair grow. And it's about 4 centimeters a year. That's the movement in Southern Ontario. So when you wake up tomorrow, or when you think about this lecture tomorrow night, your house, where you work, is not in the same place it was today. It's moved, and that process is continuous, doesn't stop. And even though it's a very, very, very slow process, and we don't see it obviously in our lifetimes, but over billions of years, you can completely reconfigure the geography of the surface of the planet. And geologists I do anyway, most of my waking hours trying to reconstruct what past configurations were like. And we use a number of different tools. I won't go into that tonight. But the continents are embedded in plates, and they are able to drift. And the plates form at what we call mid-ocean ridges. That's where new volcanism is going on all the time, and it pushes the older rocks apart. And that's the driving process. That's the fuel that drives plate tectonics. And then the plates are destroyed down subduction zones where they're pushed down below other plates, and they're recycled back into the mantle. So this is the work of a colleague of mine, Julian Lohmann at U of T, and this is a computer model. It's based on seismic waves produced by earthquakes, countless millions of seismic waves, and the transit times through the body of the planet for any individual wave are dependent on the velocity, and that's controlled by density of the material it's moving through, which is driven by temperatures and so on. So it's a complex process, but it's possible to understand the interior of the Earth from earthquakes. So whenever I mention earthquakes, you usually think of bad news, buildings falling down, people being killed, and so on. But the other story is a good one, in that we can use it to explore the interior of the planet. So this is what it looks like. So there's a core, and then you'll see these weird arms coming up, and these are plumes. And these are giant columns of hot rock. They're not molten, they're hot rock, moving their way up to the Earth's surface. And then you'll see lime green areas, and these are old plates. These are subduction zones where old crust is being recycled back into the mantle. So the Earth recycles its surface. And that process has gone on probably for about the last 3.5 billion years. And the point is that this convection process, as it's referred to, upward movement and the associated downward movement of cold crust, is what drives the plates at surface. So this is how planet Earth works. And you've no doubt got one of these lamps, or wax lamp, in your home. Fire it up and watch the wax moving up. It changes its density as it gets warmer, and that's a pretty good analog for what's going on in the deep interior of the Earth. And that's why your home is not in the same place it will be tomorrow or it was yesterday. It's because of these huge plumes that are being generated in the mantle. So this is a discovery of Thurs, what's referred to as a supercontinent cycle. So every now and again, the continents come together. They are brought together by convection, and they form a supercontinent. And this is the last one we know about, which is called Pangaea. You'll see it on the left there. And if you know your Greek, you'll know it means all the lands. So so when we have the Pan-Africans or Pan-American Games, it's all the Africas, all the Americas. Gea is Greek for land. So this is all the land, and it's surrounded by one ocean. These are very unstable. They don't remain together very long because they're being heated from below. They break up. And so that's the stage we find ourselves in today, where the oceans are still widening. Again, I gave you the rates of about the same rates the fingernails grow. But if you look at the directions in which the plates are moving, they're already beginning to converge. And Thurs had this superb, intuitive leap where he thought that this model went on. We had supercontinents forming, breaking up, reforming, and he's been proven to be largely correct. We don't know the exact number of supercontinents. We don't know the precise timing, but it's real. And it makes geology and Earth history a lot easier, because when I was an undergraduate, I was learning, like Claudia probably did, lots of stratigraphic names of rock types in Australia and India and America and all this sort of stuff. And there was no coherent guiding principle. Whereas we now know that you can group all these rocks together because the continents have a common history. So it doesn't matter where you are in the world, you've either been part of a supercontinent or you've not. So there's a commonality of history. So you can now view Earth history as a big book, and each major chapter is the history of a supercontinent. And you'll appreciate that oceans come and go. They open new oceans when supercontinents break up, and then they die as continents come together. So Earth history is really all about ocean history. Anyway, it's a nice toolkit as we go back in Earth history. And as I said earlier, a lot of geologists spend awful amounts of time trying to figure out the number of past supercontinents, where they were, and so on. So this is another diagram. It shows vectors, and I've got a question for you. Where are the arrows pointing? In where are the continents? Where will they aggregate next? And you can see it's just off China. So the next supercontinent, which if you look at the rates of movement of the continents, will be in about 250 million years' time. The next supercontinent will be in China. That'll be made in China. So they don't need to take the world over. The world is coming to them. And that in turn will break up and the cycle will start over again. So armed with that information about how the planet works, we can now go back and look again at the rocks of Georgian Bay. And the big question is, of course, you know, as any child asks in grade 4, how old is that rock? And fortunately, there is a very useful tool which we refer to as zircon age dating. Zircons have got nothing to do with zirconiums. Zirconium is an oxide grown in the lab. That's why you get big diamond-like gem quality stones. Real zircons are small. They're about the width of a human hair. And they are formed as a result of volcanic activity. So they form in igneous rocks. And they are very useful because their crystallography, their structure, is what we call tight. It doesn't allow material to leave. It doesn't allow material to enter. So it's a closed system. And when these crystals are formed, there's an unstable isotope of uranium, uranium-238. I won't bother you with the chemistry. It's unstable, it's radioactive, and it breaks down, and it produces ultimately a type of lead-206. So it's possible to measure the amount of lead-206 in this tight crystal and get some idea, quite precise idea, about how old that zircon has been in existence. And the next diagram, next shot, is a cross-section through a couple of zircon crystals on the left, and you can see they've grown through time, and as small as they are, it may have taken millions of years to grow, so you can see these growth rings. And then the other around the core, and then the other thing, you can see these little black holes, and that's where it's been probed by a laser beam, and the plasma has been fed through a mass spectrometer, excuse me, and that measures the amount of lead, and that technique was developed by Tom Crow at the University of Toronto, zircon age dating, and that's now done routinely in numerous labs around the world. And since the 70s, there's been this identification of what's called the magic numbers. So if you look at all the zircon age dates that have been produced, you plot up them in order of age, you find that they group the magic numbers. It was long before anybody knew the significance of the magic numbers. And now we realize, of course, that volcanism and the production of zircon crystals tends to be at a maximum during the formation of supercontinents. So these spikes, the magic numbers, are telling us about the age of past supercontinents and the number. And geologists give them a name. So we've already had Pangaea, that's the last one. There was an earlier phase of that we call Gondwana, when all the southern continents came together. and then Rodinia about 1 billion years ago, 1,000 million. And then there's one earlier than that called Nuna, sometimes called Nina. And then the earliest one we know about is Superior, and that's actually named after the rocks in northern Georgian Bay, Superior. Another name is Slavia, because the same rocks occur in South Africa and Europe. So they're the main supercontinents, and we're now going to look at the geology of Georgian Bay. And Georgian Bay is unique because it records 4 supercontinents, and I can't think of any other place in Canada, any other place around the world which records in such a small area the activity of 4 supercontinents. So think about geology as a book. So we have the geology of the North American continent, very, very complicated. People knew about the geology for about 100 years, but they didn't know until plate tectonics came along just how it's been put together. So you can now deconstruct the geology of North America like you can a novel. What are the main stories? Who are the main characters? What were they trying to do? What are the subplots? And if you deconstruct the North American continent, you can break it down into 5 large pieces. Each piece is complicated. It's made up of smaller pieces and so on. But there's an area there, 1, and that was brought together, assembled during the first supercontinent, which we call Superior Slavia. And if I can get out the way, there's a little red star there in an area we call the Slave Province, and that's the initial kernel, if you like, or the germ of the North American continent. That's where it all started about 4 billion years ago, and it's rock we call the Acasta gneiss. So North America has grown in size by about 70 times since 4 billion years ago. And then we had the Southern Province. That's a huge, massive crust. So that's what you see in the Grand Canyon if you go down to the river. And that came in and abutted the Superior Province. So that's a growth phase of North America during Nuna. And then we had the Grenville orogeny, and that's about 1 billion years ago, and that's associated with Rodinia. And then we had a Pangaea, and all eastern Canada was added. Most of maritime Canada is what we call out of Africa. It's made up of African crust that got stranded in North America when Africa collided and then broke away, leaving a lot of crust behind. So when you see these nice red rocks of eastern Canada, they're exactly the same as what you can find in Morocco. And then 5, the Cordillera, where all the flooding's been this week, and that's been added. All that huge area has been added just in the last 200 million years, since the breakup of Pangaea and North America beginning to drift westward, and it picks up smaller crustal pieces like a vacuum cleaner. So Vancouver Island is a huge piece of crust which is in the process of accreting to North America. So we can deconstruct the continent, and you can see there's an area in red there which identifies Georgian Bay, that we are at the boundary of 3 supercontinents. The rocks are 3 supercontinents, but the 4th one, the Appalachian one, the so-called Pangaean supercontinent, also affected Georgian Bay. So this is really unusual in the annals of geology. It makes Georgian Bay a unique place. So I'm going to go through this very quickly. There's different colors on there. Superior, about 2.5 billion years ago, in this sort of light brown color. Wawa, Timmins, Kirkland Lake, extending almost down to the shore of northern Georgian Bay. And then in red, we have the Panokian Fold Belt, like Cloche Ranges, which you drive across as you go north on Highway 6 out of Little Current. And that records the collision and the assembly of Nuna. And that's an event we call a Panokian orogeny. So an orogeny is Greek, and it means to build relief. So we talk about the Himalayan orogeny, building huge mountains, building relief, and an orogeny is essentially a plate collision. So we talk about the Panokian orogeny. And then in brown there, we have what's called the Grenville province. And they're made up of rocks that were brought together very violently during the construction of Rodinia about 1 billion years ago. And then in blue, right at the bottom there, the cover rocks, the sedimentary rocks that I touched on much earlier, they are the product of the Appalachian orogeny and the building of Pangaea. So we have a huge chunk of Earth history preserved around Georgian Bay, which makes it so fascinating. So this is what happens when supercontinents grow. We get orogeny. These are plate collisions, and the crust is thickened. It's uplifted to form these huge mountains. And this is what Ontario would have looked like numerous times in the past. Mountains have been worn down by erosion, all the sediments lost and deposited elsewhere. But the modern day Himalayan orogeny, where India has crept up northwards, you can see its former position 24 million years ago, 12, and it's colliding now. That results in the death of an ocean, because there was an ocean between the Indian subcontinent and the Eurasian plate to the north. So if you go to the top of Mount Everest, you have to cross the famous yellow band, which is a series of limestones. And those limestones are precisely the same age as the ones exposed along the Niagara Escarpment, except here in Canada, they've sat, they've been relatively undeformed, whereas in the Himalayas, they've been caught up in this vice as India has moved north. So they're now up almost 8,000 meters above sea level. Same rocks, same fossils, but a testament to plate tectonic activity. So this is the northern part of Georgian Bay. This shows the La Cloche Mountains, La Cloche Ranges, and you can see that the rocks have been bent and folded north of Little Current, and this is a fold belt produced by plate tectonic collisions during the formation of Nuna about 1.8 billion years ago. This is the so-called Panokian orogeny. Moving on, this is what the world looked like, as far as we know, about 1 billion years ago, and this is the assembly of Rodinia. And you can see a North American continent, at least an ancestral continent, which is called Laurentia. And it's colliding with Amazonia, which today makes up northern part of South America. And Baltica, which is Scandinavia, lay offshore. And again, you had Himalayan-sized mountains shown in brown, crumple zones, fold belts formed as these separate land masses came together. So this is what this area in red box here is the area which today is Georgian Bay. I should add that Georgian Bay itself is the bay proper, the bay that holds the waters in, is quite recent. It's a result of glacial scour. So it didn't exist prior to about 2 million years ago, okay? So if you look at the geology of the so-called Grenville province, you'll find it's made up of far-traveled pieces of crust. Well, it's like a complex jigsaw puzzle. And these were pre-existing smaller land masses, something about the size of Japan, which were pushed together and accreted to form this Grenville belt. And these are called terrains. And a terrain is a piece of far-traveled crust that's now embedded in the interior of a continent. So there are the ages. You can see there's older terrains in the north. They arrived first. Younger terrains down in the southeast. They were the last to arrive. And the product that you see today is, of course, banded gneisses. These are the typical rocks you see on the east and northern margins of Georgian Bay. These are beautiful rocks. And you can see why the word banded is given. And these formed under great heat and pressure. These are the metamorphic rocks that Coleman worked on around the turn of the century. And these are, of course, attractive to artists. Ed Bartram, John Hartman, and so on have painted these for a long time. Very attractive rocks to work on highly deformed, but we can do some clever stuff in the lab, and I'll move through this quite quickly. But if we do experiments in the lab with high pressure, high temperature ovens, we can grow minerals. And so we can determine the precise temperature range and pressure range that each mineral will grow. So we can go out in the field, we can look at these highly metamorphosed rocks, the gneisses and other ones. We can identify the minerals, and then by reference to charts and so on, we can say, yeah, this mineral grew when this rock was being subject to pressures of maybe 8 kilobars, 8,000 times atmospheric pressure, and at temperatures as high as 800 degrees centigrade. Garnet, for example, in the lower right there, you'll see these beautiful red garnets. They're very common in the rocks around the shield of Georgian Bay, and they form under very, very precise pressure temperature envelopes. And the key thing to take away from this figure is the depth. So if you look at the right-hand side of these charts, you'll see depth in kilometers. So what you're walking over, what you're seeing around the shield in Georgian Bay actually formed at depth sometimes as much as 35 kilometers. So you're looking at the roots of these very, very high mountains. And the mountains have been eroded off, have been destroyed by glaciers, rain, snow, over millions and millions of years. It takes about 200 million years to destroy a big mountain. And the roots are then exposed at surface. So this is a window. Georgian Bay is a globally significant window into deep crustal processes as plates collide. And geologists come from around the world to look at these rocks, because otherwise they're inaccessible in modern day erogenous. So Georgian Bay is a very important laboratory for studying these very deep crustal processes. So next time you go out and you look at these very, very complexly deformed rocks, well, they're deformed because they were essentially like hot toffee. They weren't melting, they were close to it, but they were able to deform at depth, and you get these curious folds and so on. This is where the soft rock has been sheared out. And it's this layer, about 35 kilometers down, this soft toffee-like layer, which allows the overlying plate to move. So it's like a skater or a skier actually skating or skiing over a very thin layer of water, pressure melt water. This is the smoking gun of plate tectonics. It's this stuff able to deform at very high temperatures and pressures that allows plates to move. So again, it gives us key insights into the workings of plate tectonics, and that's right here in our own backyard of Georgian Bay. So this is a slightly different scale. This is the eastern side of Georgian Bay. You can just make out O'Donnell Point. O'Donnell Point, for any boater, will give you pause for concern sometimes, because this is where you have to take your boat outside the inside channel, and for a few kilometers at least, go out into the bay before you can take refuge in the inside channel. And I am probably, most of you who do boat on the bay have had some pretty unpleasant experiences at O'Donnell Point. But the morphology of the bay, the shapes of the islands, is picking out the boundaries of these terrains. And the margins of the terrains are called shear zones, and that's where these metamorphic processes were most intense. And so you can drive up Highway 400, and you've got to be careful driving as a geologist, because you always want to look at the rocks. And what you're looking at is a whole series of these shear zones. So this is where rocks have been thrust together, metamorphosed, and then you can see pink and orange bands that strike vertically through the entire rocks, and these are dikes. And this is telling us that locally, at least, some of these rocks were beginning to melt and produce magma, and the magma was escaping to the surface through cracks, and it would take millions of years to cool, and they're preserved as these dikes. So you're looking at rocks that formed 35 kilometers down, and all the overlying strata has been removed by erosion. I always get asked, where did that detritus, where did that sediment go? And it's been established that there were big rivers at this time, and they took most of this sediment out west to the then coast of North America, which lay at Calgary. Remember, everything west of Calgary, all that big area I showed you earlier, has been added recently. And if you drill down very deeply, you find these very old sediments. And that's the reason I did remember why there's no mineral deposits in Georgian Bay. Most mineral deposits are associated, or at least deposited, by very hot hydrothermal waters circulating through rocks, and they tend to be richest towards the surface. All those rocks have been eroded, they're gone. So we're looking at the mineral-free, sterile, for the mineral geologist, deep crustal rocks. So that's the reason why Alexander Murray was unable to find any significant mineral deposits. It's all been eroded off. So let's wrap up this exploration of Earth history. This is the last go around. This is Pangaea, and North America looked very different because most of its surface was underwater. And again, there's a red box there showing where Georgian Bay is now. It lay under very shallow warm water seas, and this is where all those sedimentary rocks, the limestones in particular, were deposited. So this is typical limestones. These are students being taught how to log these rocks, how to describe them, how to correlate them. They're learning their trade as geologists. And for the first time in the rock record, we see rocks that are completely dominated by the remains of organisms. And there's an artist's impression of a seafloor at this time. Early, very leathery fishes. You wouldn't have eaten them at all. Some of them didn't have teeth. There were cephalopods, squids, trilobites, sponges, mussels, brachiopods, other shellfish. But the big rock builder is the humble sea lily. These are these things waving like kelp on the seafloor. And they grow to heights of 8 or 10 meters or more, wafting around in the water. And then you get a big storm, and it would break them. And many of the limestones that we see in southern Ontario, particularly those along the escarpment, are made out of the remains of the stems of these crinoids. They're like washers, a nut and bolt, like washers, where the stem has been broken up. So this is the first time in Earth history we see rocks that are made up the remains of fossil organisms. And this is where oil and gas becomes important, because this rock has porosity. There are very small holes, pores. And if those pores are connected, that rock is said to be permeable, and it allows fluids, it allows gas to move through it. And some of the rocks have oil, they still do. And the first international oil company, Imperial, was set up at Petrolia in southwestern Ontario, where oil was found at very shallow depths. So this is a big deal in terms of Earth history. It's also a big deal in terms of economic deposits. We now have rocks that can trap oil and so on. So this is the scenery of the limestones. This is the eastern coast of the Bruce Peninsula, halfway Log Dump Bay, one of my favorite places. The other favorite place is, of course, Cup and Saucer Trail on Manitoulin Island, which is again the face of the escarpment. Fabulous place. Though you got to be a little bit careful there for obvious reasons. We did some droning up there a few months ago, and it was quite scary looking at a computer screen standing on one of the tops of one of these cliffs. I don't really want to repeat that exercise. Okay, now last chapter. And what does that consist of? It consists of climate change, not climate warming, but climate cooling. And the last 2.5 million years have seen these repeated ice sheets form over Georgian Bay. And these are not the ice sheets you think of when you talk about an ice arena or anything like that. These were 3, maybe 4 kilometers thick. They were so thick, they took tens of thousands of years to grow, and they were so thick that they actually pushed the crust down underneath by several hundred meters. So these were enormous ice sheets. There's one in the west over the Cordillera, the Western Mountains. The one over central Canada and Georgian Bay, we give the name of Laurentide ice sheet. And there's another one up north in the Arctic. And there is a little one in Newfoundland. Newfoundland always has to do its own thing. So there's a little ice cap right over Newfoundland. But it's thought that these ice sheets grew possibly many tens of times. We don't have a good understanding of precisely how these ice sheets and when. But we're now starting, as a result of work around Georgian Bay, to have a much better idea of how they flowed. And if you go down to Antarctica, if you go to Greenland, these are not simple ice sheets. And these are composed of what we call ice streams. And these are corridors of ice, sometimes 100, 150 kilometers wide, several hundred kilometers long, which are very fast flowing. And when I say fast flowing, I'm talking about 10 kilometers a year, which is the speed of light for a glacier. And these are the areas shown in red. And what they do is accelerate erosion at the base of the ice, because the ice, in the ice, there's debris, there's rock debris, it's like a gigantic sandpaper. And so if you've got ice that's moving very, very quickly, you can get very deep erosion of the underlying rock. And this is now thought to be the origin of Georgian Bay. So we're slowly closing in on the question, how did the Great Lakes form? It's a result of very deep biting, very deep scour by these very fast flowing ice streams. And this is on the east coast of Georgian Bay, Henvey Inlet, and you will see grooves and ridges in the rock. And these are left by fast flowing ice streams. So this is a direct record of the fast flowing ice that cut down into the rock to form the basin that we now call Georgian Bay. And we're now starting a research program to map these surfaces through the Great Lakes, and we're using LiDAR. Some of you have probably heard about LiDAR. It's using laser beams to map topography. So you fire a laser beam, it's like a flashlight. Firing a flashlight at a wall and you see the reflection, that light's reflected back to you. And if you can measure the time it takes, the two-way transit time from the flashlight to the wall and back, you've got an idea of distance. So you can go into Home Depot, Canadian Tire, and buy a laser measuring tape for about 20 bucks. Well, a real LiDAR measuring device is a little bit more expensive, but it's basically the same idea, and we can now put them underneath drones. And these are two examples that we collected in the last year of LiDAR maps. You can see roads. This is in eastern Ontario, near Kingston. You can see Highway 401 there. The one on the right is of the Shield, and you can make out Highway 28, sorry. And you'll appreciate that we can now see the Earth's surface in hitherto unseen detail. I always refer to it as a Christopher Columbus moment. You're seeing new land that nobody else has seen. And it's all because of this new LiDAR technology. So it's like, in many ways, the invention of the microscope. You can see things that you couldn't see before. And we're now starting a program in Georgian Bay to map the entire area, to map ice streams, and to better understand these ice sheets, because we need to know that for mineral exploration up on the Shield. There's now, as you all know, talk of the green economy. We're going to need to find strategic minerals in quantities 1,000 times more than what we're mining at the moment. And Canada leads the way. We have this mineral-rich Shield, but it's been glaciated, it's been covered in glacial sediments. We need to know much better how ice sheets eroded debris, and then we can look at the chemistry of the debris and link that back to the source area, and hopefully get rich and find a mine. I've never done that, that's why I'm still teaching. So So this is where I'm coming to an end now. This is a map of Georgian Bay. There's a blue lake there, and these lakes were much bigger than the modern Great Lakes because the drainage out through the St. Lawrence was blocked by ice. This was about 11,000 years ago, and this is where humans, as strange as it may seem, this is where humans first begin to appear in Georgian Bay, about 11,000 years ago. And this is the big lake. It's called Glacial Lake Algonquin. It's ice dammed. The water flowed out through North Bay, down the Mattawa River into the Ottawa River, and you can see it's a much larger lake. And early humans coming in from Asia, small hunting parties, chasing caribou herds, lived along the shoreline of this lake. And I'm very grateful to a colleague, Peter Stork, at the Royal Ontario Museum, for this beautiful rendition of what it would have been like at that time. And this is where mining starts in Georgian Bay about 11,000 years ago, because they would have needed arrowheads, scrapers, knife blades, and they mined chert, very silica-rich rock. It's akin to flint from the base of the Niagara Escarpment. So there's been a long history of human occupation in Georgian Bay by successive cultures, and mining by guys that knew their geology. They were geologists about 11,000 years ago. So there's the shoreline of this big lake down on Blue Mountain. So if you go skiing down Blue Mountain, you're going to be skiing down over the old shoreline of Glacial Lake Algonquin, which is marked by the white arrows. So I'm going to end on a warning. Rocks can be addictive. You got to keep off them. But should you get addicted, we can help you out. There's a group of us, a small steering committee, and here I give a shout out to Tony Piggott, Cam Broman, and Stuart Spears, one of your own local people, with the suggestion to set up a geopark. I think, I've gone through the geology of Georgian Bay very, very quickly, but you can see it's unique. It records 4 supercontinents. There's a very strong cultural history of associated with landscapes and geology and so on, which I only briefly touched on. But nobody knows about it. So here it is in our own backyard, and these gentlemen who are now part of a steering committee have come up with a suggestion that we form a UNESCO Global Geopark. And this would, through education programs, tell people about the story of Georgian Bay, the great geology, all the cultures that have used the bay, and develop geotourism. And there are 5 of these parks in Canada. It's quite, as you can imagine, it's quite an involved process to get one of these parks set up. Tony led the charge, and Georgian Bay is now an aspiring UNESCO Geopark. It got through the National Committee in Ottawa. There's a lot of hard work, so I think the term perspiring global geopark is more appropriate. But this is a vision for the future. And if you look at all the 5 other parks in Canada, if you look at all the other geoparks around the world, Georgian Bay is right up there. It's unique because it does record such a great length of Earth's history and some pretty big events in that history. So it would be, if it's successful, and this process is going to take a number of years, it would be the largest geopark in Canada. It's about 15,000 square kilometers. It would be the whole of the bay. And I can't underestimate that the geology, culture, the ecosystems that are dependent on the geology, on the physical landscape, are globally unique. And as I explained very briefly at the beginning of the talk, I think they help shape a unique Canadian culture. They're certainly Confederation and so on. Georgian Bay has been instrumental in the history of our country. So as I say, it's now an aspiring geopark, and if this vision comes to fruition, there would be educational outreach in schools to the public, and who knows, there may be a geopark center, which would be the focus of all geopark activities. So I think I'm going to finish on that rather hopeful note and invite questions about Georgian Bay, if I haven't put you all to sleep.
No, that was fascinating, Nick. Now, I think just before we have some questions on the chat, but I think I'm going to see about stopping your screen share so we can see some people. Okay, I think we should be back. Now let's see if we can get we'll get a gallery view going. I'm going to spotlight you.
Okay, I can see some of the questions on the chat.
Yep, if you open that up, maybe deal with the let's go back and deal with the earliest ones first. That was me. That's a facetious one. That's
No, it's a good one. It's called Pangea 2. Pangea 2.
Pangea 2?
Yes, it's highly original. Pangea 2.
Don't we need something more original?
Yes, we'll come up with it. I'll invite suggestions on a postcard, and you can send them in, and I'll pick this one.
Well, we have one suggestion here. I'm not sure why. Reed suggested Trumponia, just maybe to get under his coat. He can't say China either, and he doesn't like them much. Anyways.
Well, they do tend to break up, don't they, eventually? So.
And Jip Diening is wondering, how is the Earth's rotation related to plate tectonics and their movement?
Yeah, that's a good question. The short answer is that the movement of plates around the surface, subduction, the changing of mass at depth as you push plates down, the formation of big ice sheets, it affects the Earth's rotation. Yes, good question. Not in a noticeable way, but it does affect it because you're shifting mass around.
I think Joop was wondering though when I read the question, like the mass. He's wondering whether the rotation actually affects the movement of the continents. I'm not sure that it would be a strong enough force.
That's a good question because in the early history of continental drift, it was thought that it was the rotation of the Earth that caused the continents to drift. And there was this process called pole flux, which was the flight from the poles, sort of centrifugal movement as the Earth spun, and people looked at the physics, and the process is real, but it cannot shift the crust. It's too weak. So that's a good question.
And sorry, just playing with my screen here. Why are Southwest Ontario sedimentary rocks not as prolific oil and gas reservoirs as Alberta rocks? Is that the case, or is it more? Are they not getting their oil from deeper down somewhere with this fracking and stuff?
They're older rocks, and they're fractured. They've been affected by they've been more affected by the movement of the North American plates, neotectonic processes, faulting, and a lot of the oil and gas has simply escaped. It's called outgassing. And also the geology is very different. So the reservoirs below southwestern Ontario, below Lake Erie, tend to be much smaller than the ones out west. So that's the simple answer.
Simple is good for this group, I think. Some of the stuff you told us is it's hard to get your mind around it, but we work hard. How did the ice sheets form? Why did they recede?
That's a really good question too. So that was always a big puzzle. Why do we get these big ice sheets? Why did we get up to 50 of them in the last 2 million years? And there was a Yugoslav astronomer by the name of Milankovic, Milan, like the Italian city with Kovic at the end. And around the turn of the century, he reasoned that the elliptical orbit of the Earth around the sun took the Earth further from the sun. And also the Earth is tilted, and that changes. And he said, okay, that means the amount of solar energy reaching the planet is going to be more or less. And by hand, he computed the changes over the last 2 million years or so. And he showed these graphs of increased energy, lowered energy. He said that explains the ice ages. And everybody poo-pooed it because at that time there was only known one ice age. And then people started going out into the oceans and taking long sediment cores from the bottom of the oceans, where there's been a long record of climate and sedimentation. And in the late 60s, they confirmed these so-called astronomical controls on ice sheet growth. So just bung in Milankovitch in Google, and he's one of the great scientists of paleoclimatology, ancient climatology. So the reason why they form is that because there's differences in the amount of energy that's being received on the Earth's surface.
Now, it sounds like there's great strides being made and things to be discovered even within our lifetime in geology.
Yeah, and if we can get this geopark set up in Georgian Bay, a big part of that will be much more research. So these geoparks have to be in areas where there's a lot of potential for new discoveries. And Georgian Bay is fantastic for that. I know somebody said, where would the center be? And it might be in Midland.
Yeah.
That'd be nice. Where are we going to put it, though? We got all sorts of. I think we've got a bit of a controversy with a new development proposed from our waterfront, and I think they want to put a whole bunch of condos there. I think I'd rather see the Geopark Center there, surrounded by a nice little park. Wouldn't that be beautiful? And somebody says, Steve LaForest says, your Geopark building looks a little more extravagant than our dear old U of T mining building.
What a cheek.
The U of T mining building is smack dab in the middle of Spadina, isn't it? Or
it's now the Son mining building. I spent many years in that place. It's an old, beautiful heritage building, but it wasn't designed for modern teaching. And in fact, Tuzo used to stride the hallways of that building and give very, very popular lectures there. And there used to be huge fights. You wouldn't believe it, but there used to be fights at the end of the lecture because a lot of the geologists didn't believe him. They didn't believe in continental drift. And there's excellent records. There's big slanging matches between Tuzo and more traditional colleagues.
Well, you told us about how much beer these geologists drink, so I can imagine they would get kind of volatile.
Yeah, it's a tradition that continues.
Lois Palmer asked, do you have any insight on the potential risk from TC Energy's proposed pump storage project in Meaford?
No, I don't actually. I'm not up to date on that. I don't know anything about that.
Okay, fair enough. Now, if anybody has a question they want to ask in person, now's the time to unmute yourself and speak up. While we wait for people to screw up their courage, I wondered, I think you were talking, I don't have my terms, you were talking about our area when all these little Precambrian creatures, we were covered by this Precambrian sea.
Yeah.
Why did we get flooded at that time? Was there and not at other times?
Okay, that's a good question. When you barge all these continents together, you get high mountains, such as the Appalachian Mountains. They record that event, the Appalachian orogeny. But what you're doing is loading the crust, because you've now got high mountains, which are a significant load. And what they do is bend down the edge of the plate, and they push it down below sea level. So that's thought to be the origin of these vast inland seas. And I forgot, I do apologize, but I forgot to point out that Georgian Bay at that time, or what will be the future Georgian Bay, was then at the equator. So these were warm tropical seas, not very deep, probably several tens of meters, and very, very rich in life, something like a modern reef. And most of these communities would have been reefal communities where the crinoids, those sea lilies, when they get broken up, actually build the reef. And these reefs are shaped by storms and currents. And as you go up the Bruce Peninsula, there are limestone surfaces that you can only see from air photos or LiDAR, where you can see the shapes of the original reefs. So if you go down to the Caribbean, or like our friend Reed down in Florida, go diving and snorkeling off the Florida coast, that's about as close as you get to what it would have been like in Ontario. So I think we're all going to come down and visit Reed and have a
Hey, Nick, I wanted to ask you about the Limestone Islands,
Yes.
which are about 7 miles out from the edge of the rest of the Precambrian islands, out from Point of Barrel. They're just an outcropping, I'm assuming, from the limestone base coming all the way across from the Bruce Peninsula.
That's bang on. They're called an outlier. Little remnants of rocks which are now preserved sitting on the shield, but they are far removed from the escarpment. The escarpment's retreated back to the west because of glaciation. And it's pieces of evidence like that that lead us to think that much of the shield was covered by these warm seas. There's other instances of the same rocks up at Temiskaming in Quebec, further north. So they're outliers, little pockets that have survived erosion.
And we've been out there, and of course the plants that grow there are entirely different than what grow on the shield, and are great places for the seabird colonies. But we've been out and done lots of fossil collecting on there.
Yeah, there's wonderful examples of almost like giant squids out there, preserved in the rocks. Big cephalopods. It's a marvelous place. You've got to be out there in good weather, though.
Yes, that's true.
Now, Bob Codd, did you have your hand raised?
I do. I don't have any specific question, but I'm really curious to learn more about this whole concept of a geopark.
Yeah.
I mean, what will it do for the region? Who approves it? How does it become a geopark? I mean, is there a governing body that decides whether yes or no? Anything you can tell me, I'd love to hear it.
Yeah, I've gone through it quite quickly. It doesn't happen without the buy-in of local communities and local cultures, and there's a lengthy application process if everybody's agreed to UNESCO in Brussels, and you have to identify the importance of the area for geology in the past, the importance of the geology and landscapes to culture, and most importantly, the potential for further research that can be done in the geopark. So it's a long process, and we're looking at 5 years maybe, but there has to be buy-in from communities. But a big part of the geopark is for education, and that we get a lot of visitors to Georgian Bay. We get a lot of visitors that just drive past, take a selfie, and then go home. And they're putting great pressure on some of the spots around the bay. I think we all agreed that we need a different type of tourist sometimes in other areas which are under pressure, and so this would be to develop geotourism and so on. But what I would say is get on the UNESCO Geopark website, and it's pretty impressive with what is happening around the world. And Georgian Bay is a fantastic candidate for this, but it won't happen without community buy-in.
Well, we're talking geology here, Nicholas. So 5 years is nothing, right?
Well, it is to me.
Any other questions? John Foster has a hand raised. He raised his real hand, not his virtual hand. If you'll notice, people down in your in where it says reactions. You can raise a hand there if you want to get in the queue for a question. So John, unmute yourself and ask your question. Press your little microphone, but there we go.
Yeah, I was going to ask what effect the Michigan Basin has had on the west side of Georgian Bay, and whether the Michigan Basin itself has had an extraterrestrial origin.
Yeah, okay. So let's address the first part of the question about the Michigan Basin. I talked about shallow seas that covered North America, and there were deeper basins, and the Michigan Basin is one of them. There were the Appalachian Basin and so on. But, you know, the modern thinking is that you're looking at buckling of the underlying shield into what are called arches and sags. And as a result of the crustal thickening on the East Coast when the Appalachians were being built. So, you know, the idea that there are large meteorite basins or impact basins is probably not supported by that evidence. Although, as you know, the Sudbury Basin is a large meteorite impact basin. There are several other smaller ones. There's one below the city of Windsor. There's one in the northern part of Algonquin Park, the Brent crater. But to argue that the very large Michigan Basin is a product of impact it's a bit of a stretch. Although it's a good idea.
Yeah, would that be the same as that huge ringed structure over in the Sahara Desert in Africa? Then?
It's on a scale which it would make it the biggest meteorite impact crater on the planet. The biggest one is Radeport in South Africa. It's about 200 kilometers in diameter. Sudbury is about 180. The Michigan Basin is much larger. So again, I'm not aware that anybody's actually proposed that it is a form of meteorite basin. It's more, there's people that have modeled what's gone on, and again, it's related to buckling, large-scale buckling of the surface of the shield in response to the weight that you're putting on the margin of the plate underneath the Appalachians.
So it's a geocline.
Well, yeah, that word has gone out of. That has all sorts of implications which are now dated. But yeah, sure.
Okay.
I was going to say a lot of
yes.
when we get into space exploration, that's, you know, I think the astronauts trained to be a geologist in Sudbury, and a lot of geology is kind of moving off planet. But you can't call those people. The astronauts have to know their rocks, but they can't call them geologists anymore because the geo was the Earth.
Yeah, that's right. Yep.
Reed has another question.
I do. Yeah, can you hear me? Yes.
Yeah.
Isostatic reaction is still happening in the Great Lakes Basin. What kind of scale are we looking at, and does that have does it have an impact on water levels?
Yeah, that's a good question. So isostatic refers to vertical movement of the crust in response to loading and unloading. And we just had a question about the Michigan Basin. That's response to crustal loading. But we've had these big ice sheets, and they sit on the crust, which is rigid, and the underlying mantle is pushed down and away from underneath the ice cap. So there can be depression of several hundred meters. And northern Georgian Bay is still recovering. I forget the exact rates, is very low, a few centimeters, maybe 10 centimeters a century. But the southern part of the bay is recovered. So the whole of Georgian Bay is actually being tilted. The northern part is going up, and the southern part is slowly subsiding. So Toronto is further south, is actually subsiding very slowly. So these processes are still going on. The further north you go into northern Ontario, they become very important because the ice only disappeared more recently in that direction, so the recovery is still going on. So if you go to Polar Bear Provincial Park, the province of Ontario is getting bigger every year because the beaches are being uplifted. You find these staircases of beaches. So the older beaches are higher than the modern beach.
So the second part of it, there is essentially no impact on local water levels in
No,
I think
Lakes.
Reed
no,
lost his dock this summer, so he's trying to blame it
yeah.
on somebody.
Well, the lake levels are going down now, right? But that's a different control
Yeah.
from the glacial isostatic process, which is slow.
Much slower.
It's more a climatic control on lake levels.
Right.
As you know.
Any other questions, anybody, before we wrap it up? Pat File, turn your microphone on there, Pat.
I just was thinking that some of those small boat sailors and artists would possibly be groups that might have an interest in this project idea, because some of them are very much appreciative of the visual aesthetic aspects of it, I guess, and just but I had a question about aggregate. I'm just wondering, what is it about, because when we're in the shield area, like how do we end up having places where there's this aggregate mining or digging out of aggregate, and like why does it seem like it's a problem if in terms of the impact when you sort of remove rock from an area?
Well, that's a really good question. We have aggregate pits and quarries in Ontario because our cities are growing very quickly. We have these tall condos being built in Toronto, which consume enormous quantities of concrete. You need aggregate for that. And not all rocks produce the good quality aggregate. You don't want anything too soft. So the limestone along the escarpment, some of the granites in the shield are sites of aggregate extraction. And then the problem is, once you form a deep pit or a quarry, you're actually exposing the groundwater, and you're at risk of disturbing the groundwater flow system and also contaminating that water. So it is a problem, but it's all driven by the demand for concrete. It's worth more now than some economic minerals. If you have a good aggregate pit or quarry, it's better than having a mine, actually. It's
I think part of
so
it is that
valuable.
the aggregate has to be close to where the building is going on. They don't
Well,
want
not really. Some of this stuff, as you know, is brought in from northern Georgian Bay, near Killarney. It's brought in all the way down to produce cement for the Toronto area. So it's so high value now, it can be moved over long distances. It's a problem, and that's all part of what's called the urban shadow. So the urban areas are now exerting a shadow over the surrounding regions because they require resources. You dispose of wastes, and you also have a huge demand for stuff like aggregates.
Well, I want
It is a problem.
to thank Professor Eyles very much for a fascinating talk. I think we're all going to go out and buy your new biography when it comes out. But Nick, tell us a bit more. You have some other great books about rocks if people want to find out more. Ontario Rocks and things like that.
Yeah.
What book would you recommend that you wrote?
I'd recommend the most expensive one so I can retire early.
Okay.
No, I think Canada Rocks. I wrote that with a colleague. It's a labor of love. Nobody writes books for money. It's purely to learn. And Canada Rocks, it looks at the geology of the whole country. There's a lot of history in there about how geology has affected culture. The previous question about artists and many other people finding solace in the rocks. I think it's a really important point. It's not just about rocks, it's about landscapes and how the rocks have made the landscapes. And then the other one is the Georgian Bay book. So, when you're sitting at home and it's snowing outside, your boat's all tied up for the winter, you can open the book up and hopefully it will remind you of next summer.
Now, You mentioned John Hartman in passing. Now, John and his family are members of our group. I don't think John's here tonight, or Peggy, but particularly some of those photos, the laser photos you showed, they kind of remind me of John's work. It's a beautiful area we live in.
Well, it is, and it needs conservation. People should know about it. I mean, when we talk about geopark, one of the things we're trying to do is make a virtual geopark too, so that somebody can, whether in Germany or China, they can visit the park, but not physically as well. So it would use new technology to bring the wonders of Georgian Bay to a bigger audience.
Okay, well, thanks again very much. And for people who want to hang around just a little bit longer, we're going to try something a little bit. You know, some people said they missed our monthly sightings, and it's a little trickier on Zoom, but we thought we'd try it a little bit to get people to give us their sightings, things they've seen recently. And to kick it off, I think myself and Bob Codd, we're going to share some of the things. And this is probably more birds than rocks, Nick. But you mentioned that geologists have a problem when they're driving and can be dangerous. Yeah. Birders are worse, because I mean the rock is going to stay there, but when that bird flies by, you got to slam on the brakes and make a sudden stop. But anyways, we're going to share some of our sightings, and then people can think of what if they want to unmute and share something you've seen. And when we do this, we share our screens. We thought maybe when we get to the Christmas bird count this month, more people might want to try this, share photos they have on the Christmas bird count. But I'll share my screen here first. Give me a second here to figure this out. And these are just a few of the things I've seen recently. Do you remember anybody that was on our walk recently by Little Lake? We did see one red-tailed hawk. I went back a couple days later, and I think this was probably the same hawk, red-tailed hawk, right in the corner of Little Lake. But there was actually a pair of them. And I think it's the female on the right, male on the left, hanging out by Little Lake. There's a close-up of the female red-tailed hawk. And I thought this was interesting. This is a box elder bug in Stainer. Our last email, we talked about all the ladybugs that were out in the warm weather a couple of weeks ago. And after I sent it out, we thought a lot of these bugs are looking for warm places to spend the winter, and they'll come out on a sunny day. But our forest entomologist, Paul Bell, thought it looked like it might be part of a mating, what they call a lek, all the males trying to get one last bit of mating in before winter. So this is a box elder bug adult, but I thought it's interesting. This is also a box elder bug. This is the box elder bug nymph, and the nymphs are the ones that come out of the eggs. The nymphs don't fly. Now I think this is a kind of a late stage. They grow and go through a couple of stages, but I think this guy is just developing his wings, but they're probably not functional yet. But those are the wings on the adult. So that's a box elder nymph. Enjoy, and they're both life stages were present at the same time, which I think happens fairly frequently. Went over to Aurelia late one night and saw two scoters. They're kind of a weird-looking duck scoters. This on the left is a surf scoter, and on the right is a black scoter. So it was nice to see the two species. In Ontario, we also get white-winged scoters. Sometimes you will see these on Midland Bay, sometimes, or Penetang Bay. But they're often far out. They're really sea ducks, so they don't hang around the shoreline too much. They get out where the waves choppy. There's the black scoter. There's the surf scoter. Surf scoter doesn't look unlike the white-winged scoter, but he's got a little straighter white next to his beak, and there's no white on the wing. And this is a little long-tailed duck. I spotted down in the Berry on Captain Phillip Bay. I've taken to call these, when the long-tailed duck used to be called a name which is objectionable. I'm not going to repeat it. But at the time they decided to change it, one of the suggestions was what they call these ducks in Wisconsin, which is Calathumpian ducks. And I kind of like that name. I think I'm going to call them that from now on. A Calathumpian band is a band that makes loud, enthusiastic, but not really all that melodic music, which is kind of the way these ducks sound when they get into a big group. These are redneck grebes, again on Captain Phillip Bay and Berry. and a nice common merganser male on Kempenfelt Bay and Berry, and a greater blackback gull. Kempenfelt Bay is a good spot to see kind of odd gulls. People see little gulls there, and the blackback gulls will start to gather pretty soon. So I'm going to stop my share, and I don't know, Bob, you want to show us what you got?
Yeah, I don't have a lot to share, but we can try it.
Okay.
Uh-huh. Okay. Minimize that.
I see your screen, yeah.
Okay, so this is in Hog Bay. That was what, maybe a week ago, Sue?
Yeah.
This is a post that usually we have cormorants hanging around on that post, but as Ken pointed out, once the eagles arrive, the cormorants tend to vacate the area pretty quickly. And
That's funny. In November, I don't. Well, I've maybe seen one cormorant on the. Well, most of our cormorants are gone, but if you go down to Kempenfelt Bay, there's still lots of cormorants down there. But not too many of them up around our area right now, I don't think.
we had four our subsequent visit there, so that was
On Hog
even
Bay?
more recently. Yeah, on Hog Bay. So we're speculating that this one down here is smaller and that one's the male. That's our assumption. I have no way of proving that, but this is what we're thinking.
In general, with birds of prey, the female is usually the larger of the two. Yeah.
This is a sharp-shinned hawk. This showed up in our backyard. It's not the greatest photo because it was taken through a dirty window, and but it flew in from across the road, and it seemed to be pursuing another bird, but there was no great panic, so we kind of wondered if it wasn't a second sharp-shinned hawk that flew in. This is an American tree sparrow. This is the only bird I've ever seen eating Phragmites seeds. I've seen that a couple of times. This was taken down in St. Marie Park, right at the mouth of the Wye River.
Was he eating them with relish or just kind of sampling them?
Well, actually, I think we kind of disturbed him, and he spent most of his time looking at us to see what we were going to do. And
Did you try any of it yourself?
I haven't been tempted to eat grass in a long time, no.
Because if we could, I mean, they try to get us to eat garlic mustard. If they could get us to do something with Phragmites, it might help.
I think I've gone the wrong way with my my little slideshow here, so I'll go back the other way.
Okay.
There's the northern cardinal. My apologies to people who saw your sharing email. This is the same bird, just that was in your sharing time email, but it's just a little different view. This bird posed quite nicely for us, so I just had to take her picture. This was quite an interesting sighting. We were down in Rotary Park in Penetanguishene with Heather, and we saw two of these for sure, but there could have been as many as five. They flushed rather readily. I was able to catch one photo of it just as kind of a documentary proof, but most of those have already left the scene, and the eBird police think it's rare at this time of year. So
it's a Wilson snipe, Bob.
it's a Wilson snipe. I'm sorry, I forgot to mention that. Yes. And this is, I think this photo was also in the sharing. This is an American coot. I had it, originally I had this supposedly in the Wye Marsh, or in the Wye River, but it was actually in Tiny Marsh. I went down there to take some photos of the Phragmites removal that's going on down there. And I don't think the tree sparrows can eat all the Phragmites that's down there. And this is another late season bird. So we've never seen a red-eyed vireo in November, but this one was in Wabashine on the Tay Trail. And it posed very nicely for us. We were actually looking for a golden crowned kinglet, and lo and behold, it turned into a vireo. And this is a fairly common sight at this time of year, a ruffed grouse. This one was in Midland Point on Sempresca Road. And
Yeah, they say they actually breed this time of year, so you might see some displaying.
it encouraged me to show my dirty mushrooms. So this is a stinkhorn, and I forget the long name of it. A netted stinkhorn is probably the most common name of it. It's a member of the phallus mushroom group, and for obvious reasons. I just had to include it because I'd never seen anything like this in the wild, and it was really quite a remarkable find. And I think that's all I've got to share. Oh,
Okay.
white crown
One
sparrow,
more.
because they're so pretty.
Yep.
Okay.
You want to stop sharing? And anybody else got anything they want to tell us that they've seen the last little while? Just unmute yourself or share your screen, whatever you like.
Well, we've got limcon and little blue heron and white ibis, common egret, black vultures all over the place. I'm just bragging. Never mind.
Yeah. Yeah. Florida. Yeah, still a few birds down there, eh? Anybody
There's
else?
there's palm warblers everywhere. Palm warblers spend it seems they spend their winter in this whole area here, and they are prolific.
Those are our palm warblers. Send them back.
hmm
Anybody else? Don't be shy. How about you, Heather? What have you seen? Nothing much. Well, if that's it, think about next month. Again, maybe our next meeting is going to be the wrap up of the Christmas bird count, and we thought since we're not getting together, we'd take our time and do it on the Tuesday rather than right that evening, because we'll all be whacked out from counting birds. And so we'll meet on Tuesday night, and I think as part of Dave will wrap up the Christmas bird count for it. Dave get us his contact, but I'll make sure that gets out on an email soon to volunteer as well with his contact number and email. And part of that evening too, we're going to have Kate Harries come along and do a little presentation on the Phragmites project down in Tiny Marsh. She has some interesting news to share down there. But we'll probably have some time to share photos of the count or anything else you see in the next month. So I think with that, I'm going to share my screen one more time. And since this was geology night, I have a little geology song I thought I'd share here. Let's see if I can find it.
I was going to try and share my screen after you.
Well, why don't you do yours first? Have you got it, or you can?
Well, I've never done this before, so let's see.
Okay, well, you work on it, and I'll share mine in the meantime.
Okay.
This is not my song. This is somebody else, but oh well. Okay, this is the geologic time song. Here we go.
In the Devonian there was no ozone, in the Cryogenian the earth was frozen, the Ediacaran set life in motion for the Cambrian explosion. Do. Life got bigger in the Ordovician, by the Silurian you could go fishing. In the Devonian we went on a mission on land to find room for growing and wishing. Do. The Carboniferous was fantastic for giant bugs and oil to make plastic. Permian creatures were weird but classic, and dinosaurs evolved in the mid-Triassic. Do. In the Jurassic came Stegosaurus. T-Rex lived in the Cretaceous. Roar! And they might have grown more and more when crash went the great big meteor. Do. Earth got hot in the Paleogene for the biggest snakes you've ever seen. The ice caps formed in the Neogene, and in the Quaternary came the human beings.
There we go. Okay, you're on, Reed.
That's a hard act to follow. Let's see. How do I? Okay, so I go there, and then I go.
You gotta
there.
share
I'm
your.
Anderson, and this is Environmental Science Video 3
There.
from Geology.
Well,
which is
wait a
the study
second.
of rocks and how they change over time. And in this class, more appropriately, how that
Wait a second.
affects
I gotta
human
stop
society.
something here.
Now, the problem with rocks is that they change slowly. They change over geologic time, and we simply don't live long enough to see all these changes occur.
Aha.
There we go. Okay.
Okay, see if this works. You see that?
Yep.
Yep.
I don't think we're getting sound yet. Are you on?
Ah,
Yeah, I think your videos may be muted, or.
so you can't see that?
We
Or
can
you
see it, we can't get the sound.
There's no, oh, that's because my mute button is on. What an idiot. No, it's not.
No,
No, we're hearing you, but not the video.
Oh, that's too bad. I don't know how to do it then. Okay, you'll have to teach me that.
Work on it for next month. We'll
Okay, Ken.
experiment on it.
Okay, that's great. Thank you very much. Sorry about that.
Yeah, well, we'll get to it next month. We'll have a practice session and we'll figure it out. Because he doesn't seem to be muted on the video or anything, but we're not getting the sound through. But we'll figure it out.
All right, thanks, Ken.
Okay, Susan, you want to say goodbye to everybody, or should we just wrap it up?
How do I close this?
Goodbye, everybody. No,
Okay.
that was a wonderful presentation, Nick. Thank you very much, and we'll follow the Geopark possible project with great interest. Thank you. Thank you again.